Alright, in this video we're going to talk about collision theory. Collision theory is the concept behind kinetics of reactions, how we know how fast a reaction is going to work. So collision theory relies on the idea that reactants act as discrete molecules that collide with one another. So in a reaction A plus B goes to C, A and B are reactants. Molecule A and molecule B need to collide in order to produce product C. So this need for collisions gives us our idea behind collision theory. And if we think about these collisions like billiard balls on a pool table, we can see how having more billiard balls on the pool table will give us more collisions. The more collisions we have, the faster the reaction is going to occur, because each collision is necessary to make product. So when we change the concentration of our two reactants, A and B, or changing just A or just B, it affects how fast our reaction runs. So at lower concentrations, less billiard balls gives us fewer collisions. At higher concentrations, more billiard balls will give us more collisions. When we look at writing the rate law, which was in a previous video, we said the rate is equal to our rate constant K times the concentration of reactant A raised to some power times reactant B concentration raised to some power, and we're multiplying those concentrations together. And the reason we're doing that is because of the collision theory idea. So if we take, for example, A and B, if we had two molecules of A, shown in the orange, and two molecules of B, shown in the blue, there are four possible collisions, as this molecule of A can collide with either of the blue, and then the second molecule of A can collide with either of the blue. So four potential collisions comes from 2 times 2. If we then expand it to 3 molecules of A, still with 2 molecules of blue, this gives us 6 potential collisions, 3 times 2. And if we further expand the B, 3 molecules of A and 3 molecules of B, we have 9 potential collisions, and it keeps growing. So we're multiplying the concentrations of each because of the added number of collisions every time that our concentration increases. Now, our molecules A and B not only have to collide, but there's a couple of requirements that go along with that collision. Two requirements that we're going to talk about are correct orientation of the collision and adequate energy. So let's look at the first one. Collisions must occur with the correct orientation. If we're going to have molecule A and molecule B collide in order to make product C, the A and B molecules have to be correctly oriented to one another. They have to be correctly aligned in order to make the correct product. Because A and B are really not billiard balls where they look the same in every dimension. They are molecules that have polar and nonpolar sides, reactive organic functional groups, and so we have to look at how they're oriented when they collide. So if we look at the example with NO and O3, we can have an ineffective collision if they are not oriented correctly when they collide. An ineffective collision doesn't produce product because the reactive functional groups did not align. It just gives you more reactant. However, if they do align in the correct orientation and alignment, you get the creation of the products. So our A and B molecules have to be in the correct orientation when they collide. The second requirement is activation energy. Activation energy is the minimum energy required to make the product. So just because molecules A and B collide doesn't mean they're going to make product C if there's not enough energy to do so. So this minimum energy is called the activation energy, and it's noted as a large E for energy with the little subscript A. If we look at a metaphor for this idea, we have a golfer hitting a golf ball over a mound in order to get to the hole. She only has to provide sufficient amount of energy to get the ball to the top of the hill, because once it's at the top of the hill, the ball can roll down the hill due to gravity to get to the hole. The same idea is true for reactions. We have to provide sufficient energy for our molecules to get to this halfway point or transition state in order to make product. Activation energy is that energy required to get to that point. In terms of a reaction graph, we can see where this comes in. So we have potential energy along our y-axis and our reaction pathway or progression along our x, where we're starting with our reactants, and this is the energy associated with our reactants. And then on the right side we have our products, where we want to end up, and the potential energy associated with the products. So in order for our reactant to turn into product, we first have to deform the bond. So you can see in this example, this is a linear molecule. We first have to provide sufficient energy to disfigure the bond, deform the bond so it's breaking apart. Because we have to break this carbon-nitrogen bond in order to form a carbon-carbon bond for our product. So this deforming of the bond requires energy. So energy is going in. The amount of energy necessary to get to the top of this peak is that activation energy. Once we get to this peak, this activation energy amount, we then have what's called an activated complex. We have created a halfway step where we've broken the original carbon-nitrogen bond, but we haven't quite formed the carbon-carbon bond that we need. But as we go down the hill on the other side, energy is being released as we form the new carbon-carbon bond, and we start to reform the correct structure for the bond so that our product will again be linear by the time it gets down to the correct orientation. Alright, so this is a reaction graph or energy graph showing the activation energy requirement for this particular reaction. If we had a scale, we could get a numerical value for this. And we also see our delta E. Because this is potential energy, this is our difference in potential energy between the products and the reactants. So why do we have to have a peak? Why do we have to deform our molecule and get this high energy state? This comes from the idea of the transition state theory. In order to get from reactants to products, there has to be a halfway point. There has to be a point where we are breaking bonds from the reactant and forming the new bonds for the product. This halfway point, because it requires partial bonds that are being broken and partial bonds that are being formed, is highly unstable. Probably not an actual stopping point if we think about a reaction. It's not an intermediate step. And it's what we call the transition state. Right? Because it's so unstable and high energy, we have to make sure we have sufficient energy to get to that point. So in the transition state, at the top of that peak, we have partial bonds from the bonds that are being broken in the reactant, and we have partial bonds that are becoming the new bonds for our product. And the transition state is really just a hypothetical, imaginary halfway point, what this must look like if we're going halfway. Most of the time, this transition state or activated complex is completely made up. It's what somebody imagines halfway must look like. And there could be multiple ideas of what a halfway point would look like. And in the end, it doesn't really matter what we visualize when we think of this transition state. We can measure the energy required to get there, and so we know the activation energy for the process. The other thing to realize when we talk about the top of this activation energy curve is that when you get to the top of this hill, you don't have to go to product formation. It's not simply a one-way reaction for most processes and reactions. Reactions can go forward and in the reverse direction. So once it gets to the top of this hill, our reaction could go back the other way and reform our reactants, or it can continue forward and make our new products. So let's look at some examples that we have. In the graph on the left, we see our reactants, 2NOCl, going toward our products, 2NO plus Cl2. We can see the activation energy going forward, so going up to this transition state, this top of the curve, and our capital EA for the forward reaction shows our activation energy necessary to get to this point. And then if it continues toward our products, we see the energy decreasing as our products are formed till we get to our potential energy of our products. Now, if our reaction were going in the opposite direction or the reverse direction, we would start with our 2NO plus Cl2, and we see our activation energy for this direction. We get to the same transition state we had before, the same activated complex, because our halfway point looks the same regardless if we're going forward or backwards. And then going in the reverse direction, we have a decrease in energy going back to the 2NOCl. So we have two different activation energies if our reaction is reversible. We have activation energy of the forward, energy needed to get to the transition state from our reactants, and the activation energy of the reverse, the energy needed to go to the transition state from our products. And then we have our delta H representing the difference in these potential energy levels between the reactant and the product. In this case, since our product going forward has more energy than our reactant, this would be an endothermic process, and our delta H would be positive as we do final minus initial values. If our reaction is going in the reverse direction, we would have more energies to start with and less energy in our final position, indicating an exothermic reaction, and our delta H would be negative. The transition state here shows what a potential hypothetical imaginary activated complex might look like, where we're breaking the nitrogen-chlorine bonds for two molecules and forming the chlorine-chlorine bond. The graph on the right is very similar. We have a forward reaction activation energy, reverse reaction activated energy. We have our reactants going to the transition state where our partial bonds exist, for where we're breaking our bond between our two oxygens of the O3 and forming a new bond between the oxygen and the nitrogen, and then a decrease in energy as we go to the products. This forward reaction would be exothermic because we end up with less energy than we started, and the reverse process would be endothermic. Alright, so let's think about what could affect the rate of our reaction. So if our reaction is based on collisions, we already can see how changing the concentration can affect our rate. We can also change the temperature to affect the rate of the reaction. If we change the temperature, we are changing how fast our molecules are moving. The faster the molecules move, the more potential collisions we can have. Also, if we increase the temperature, there's an increase in kinetic energy. There's more energy in the collisions, and this translates into more of our collisions having that activation energy necessary to make product. So again, that's going to increase our rate of reaction. Generally, most reactions see an increase in reaction rate with an increase in temperature, and it's normally fairly obvious. In fact, most of our reactions have an exponential relationship between our temperature and our rate constant. And our rate constant is where we see this reflection of temperature, and we'll talk about that. The rate constant K that we've noticed before in our rate law is constant for a given process at a given temperature. But as we increase temperature, we're going to change K as well. Alright, so let's look at our distribution of our collisions. So if we're imagining our molecules A and B moving around very quickly, colliding into one another to produce product, we can also see how the amount of energy in the collisions is going to change when we change the temperature. So if we look at this graph, our y-axis is our fraction of molecules. So this is the number of molecules we have that have a certain amount of energy in their collisions. Versus, on the x-axis, our kinetic energy. So at a particular temperature, we'll look at the blue line first where it says lower temperature, we have a distribution of molecules that have different amounts of kinetic energy. So small group of molecules have very little kinetic energy, larger amount have a moderate amount of kinetic energy. Here's where you might see our average if we're looking at the area under the curve. And as we move to the right, we have a very small number of molecules that have sufficient energy to form product from a collision. And the dotted line here represents that activation energy, or minimum energy needed to make the product. So only the area shaded under the blue curve represents the number of molecules or fraction of molecules that have sufficient energy to make product. Now if we raise the temperature, that increases kinetic energy of all of our molecules, so we see a shift in our graph toward the right. So an overall increase in kinetic energy. More fractions have higher amounts of kinetic energy, so we see that more molecules are past this threshold of activation energy, and we have a larger area that is shaded under the red curve. So more of our molecules have sufficient energy to make product from collisions. And if we continue to increase this temperature, we would continue to see this graph shift to the right. The mathematical expression for this is given here. F represents our fraction of molecules equal to base E raised to the negative activation energy divided by our gas constant R times T. Our gas constant R is still in energy units, so this is still our 8.314 joules per mole Kelvin. Temperature has to be in Kelvin, and our activation energy is measured in energy units of joules or kilojoules. So filling in our temperature, our gas constant, and our activation energy for a reaction, we can calculate the fraction of molecules at that particular temperature that would fit under the curve. And this is part of the Arrhenius equation. So the Arrhenius equation looks at the relationship between rate constant, K, and activation energy and temperature. So how was the temperature affecting the rate? It affects the number of collisions because our molecules are moving faster. It affects the number of successful collisions because more of our collisions have sufficient energy to make product. And that is reflected in having a larger rate constant, K. So our rate constant K is made up of two factors. The first one being this fraction of molecules with sufficient energy, so this base e to the negative EA over RT. And the second is what's labeled as the large A here, or the frequency factor. Frequency factor represents the number of likely collisions that are in the correct orientation. So our rate constant K reflects how many molecules are colliding in the correct orientation and with sufficient energy to make product. And you can tell from the equation that this is an exponential curve. So as temperature increases, our K value increases exponentially based on base E and the activation energy. Since temperature is on the bottom of the fraction of the exponent and there's a negative out front, increasing temperature leads to an increase in K. Sometimes it's a very mild increase and sometimes it's very substantial, and it might depend on where you are in the curve. So if we look down here between 190 and 200, there's not a big difference in the K value. But between 230 and 240, or even 240 and 250, we get a more dramatic increase in the rate constant K with the same kind of temperature change. Alright, so let's look at the A term, or the frequency factor. How is this determined? So the A term is made up of two factors, Z, which is your collision frequency, and P, which is your orientation probability factor. So Z represents how many total collisions you have, successful or not, and P represents the probability of a successful collision. So if we take the example over here in the picture, let's say we have 5 potential orientations for a collision, but only one out of the 5 is successful. The other 4 are ineffective. So we would say the probability of a good successful collision is 1 out of 5. So that would be our orientation probability factor, 1 out of 5. Now if I only have 10 collisions, 10 times our 1 out of 5 would say I have 2 effective collisions. But if I have 1,000,000 collisions, using that same 1 out of 5 ratio, means I would have 200,000 effective collisions. So the total number of collisions you have is very important, and that's where the Z comes in. So our frequency factor A is equal to total collisions times the probability of a good collision. So A represents how many good collisions we have. And this has to be determined experimentally. In the next video, we'll talk about the math and how we can calculate the A value and how we can calculate K value at different temperatures.